Lab will be exploring centripetal force and uniform circular motion. Now recall Newton's first law of motion. It says that an object, such as this car that's at rest, tends to stay at rest, or if it's in motion, it tends to stay in motion at a constant speed and in a straight line unless a net force acts on it. So as this car is traveling along, if no force acts on it, it's going to follow a straight line path. In order for it to turn, and instead of being at this location here, the car is instead on the road along this curved path here. So in order for it to change directions from that straight line path, there has to be a force pulling it towards that direction. And notice that that is directed towards the center of the circle. And again, if the car is over here, headed this direction, then with no force acting on it, or no net force, it's going to follow a straight line path at a constant speed. And in order, instead of it being right here, in order for it to follow this curved path and be right here, there has to be a force pulling it along that direction, which notice it's also directed towards the center. And this change in velocity, the change in direction, even if it's moving at a constant speed, is called the centripetal acceleration. And the force that produces that centripetal acceleration is called the centripetal force. And so centripetal force is equal to the mass of the object that's moving in a circle times centripetal acceleration. And centripetal acceleration can be calculated two different ways. If we know the tangential or linear speed v, we can calculate it with v squared over r. Or if we know the angular speed, then we can calculate it with r omega squared. And so centripetal force, we can calculate mass times v squared over r, or mr omega squared. So anything that moves along a circle or curved path has a centripetal force producing that circular motion. And centripetal force has to be provided with some real physical force. So for a car moving in a circle around a track, that centripetal force is provided by friction. In other cases, such as when an object is orbiting another object, like the moon orbiting Earth or Earth orbiting the sun, gravity provides the centripetal force. So here are the things you'll need for this lab. You will need a partner. This lab will be very difficult to do without a partner. You'll also need a stopwatch, and you'll need two small objects with known mass. If you are in a class using a kit, then you have washers and a rubber stopper or other similar objects that you can use. If you don't have a kit, then you can find something around your house, and it can be anything. And if you don't have a scale for measuring the mass, then Google it and find an estimated mass. And when you record your data, just notate whether you used a scale or whether you estimated it and how you estimated the mass. You'll also need a small hollow cylindrical tube. So if you have a kit, then your kit came with one. If not, then there are several things you could use. You could take a pen and disassemble it so that you are basically just using this part here where the top is taken off. You'll be putting a string through that hollow tube. You could disassemble a pen or a mechanical pencil. You could use if you have metal straws or bamboo straws or a piece of PVC pipe, or you can look around your house and try to find something that you could use as a cylindrical tube. Now, if you have trouble finding something, you don't need to go buy anything, just contact me and we will work something out or do it together over Zoom we'll find you a partner to work with over Zoom, or we'll figure something out. In your lab report, I want you to include an objective or purpose. I want you to include a materials section. I want you to draw a diagram and label everything on the diagram. You need to include a data table. Make sure you label everything and include units. I want you to include a calculation section. Make sure you show your starting equation and the numbers that you plug in. Show your units everywhere, and then draw boxes around your results. And then I want you to write a conclusion. In your conclusion, be sure to include your specific findings, your specific percent difference values, any sources of error. Don't just write human error, and don't include calculations or math as part of your errors. Think of specific things in the experiment that could have led to errors. So the first thing you're going to do, you're going to get your cylindrical tube and your string, and you are going to place the string through the tube. Then you're going to take your two masses that you have chosen, and you are going to attach or tie each one to the string. One at the bottom and one here at the top. Now I'm going to call this one at the bottom M1 and the one here at the top M2. So if you have it set up like this, then if you let go of the string or let go of the masses, the force of gravity is going to pull downward, and it will then be flush against the tube. So what we're going to do is get M2 moving in a circular motion. So if you grab that cylindrical tube in your palm and you start to rotate it in little circles, then you are going to actually see M2 start moving in a circle and M1 will rise. Now you want to get M2 spinning where it's oriented horizontally and also where M1 is not changing height. If you spin M2 faster, then M1 will rise. If you slow down the rate of rotation, then M1 will lower, and you want M1 to stay at a constant height, and you want this string to stay at a constant radius. And so that'll take a little bit of practice. And you don't want M1 to rise to where it's touching the bottom of the tube here, because that will affect your results. Now, as M2 moves in a horizontal plane, rotating in uniform circular motion, then at this moment here, it's headed this direction. And with no force acting on it, it would continue on in a straight line at a constant speed. But because it's moving in circular motion, we know that there must be a centripetal force directed towards the center that causes it to follow the curved path. And this centripetal force, so M2, you will either measure or find the best estimate that you can. Now R, we will measure using a ruler or measuring tape, which I forgot to include in the list of materials. I'm going to come back to it in a moment. Let's first discuss omega, which is the angular speed. Let's first look at how we can measure the angular speed. So angular speed is change in angle over change in time. And remember, we can measure angles in units of degrees, radians, rotations, or revolutions. So if I take one revolution and measure the time that it takes to go through one revolution, then that would give me the angular speed. And that would be revolutions per second. But SI units for angular speed are radians per second. So to convert that to radians, I would multiply by 2 pi over revolutions, 2 pi over 1 revolution, and that would leave me with radians per second for the angular speed. Now, in this experiment, it will be difficult to measure the time for just one revolution. As the object is rotating at a constant speed, you want to pick a starting point. So, for example, when my M2 is right here, whoever's rotating it, the partner is going to do the timing. So the partner will pick a starting point and start the timer. And as this goes around, after it has gone through one complete revolution, instead of just watching it go through one revolution, you should instead watch it go through 10 revolutions. And so after it has gone through 10 complete revolutions, then stop the timer and record the time that it took for 10 revolutions and measure it in seconds. And so then we'll have the angular speed in revolutions per second, but you want to convert it to radians per second. So instead of only calculating the time that it takes to do 10 revolutions once, I want you to do it 5 times. And so you'll repeat this 5 times, each time measuring the time that it takes and the radius. And then you'll calculate the average time and the average radius. And the average time is the only one that you're going to plug into this equation for angular speed. So you're only calculating angular speed once, and that angular speed is what you'll plug into this equation up here for centripetal force. And you're only plugging in the average value of R into that equation. So you're just calculating the centripetal force once using that equation. Now we're going to calculate it a second time, a different way, and compare the two values. So if you look at M1, we have 2 forces acting on M1. We have the force of gravity or weight acting downward, and we calculate that with M1 times G. And we have tension acting upward in the string, and I'll call that T1. Now, if M1 is not accelerating upward or downward, if it's steady, then the magnitude of T1 is equal to mg. But remember, the tension is the same everywhere along a string. And so the tension that's pulling M2 towards the left, we'll call that T2, is the same in magnitude as T1. So T1 is equal to T2, but T1 is equal to M1G, and T2 is, that tension is providing the centripetal force that's acting on M2. And that centripetal force is what we just calculated using M2 times R omega squared. And so we want to find out, are these two values equal? So is the centripetal force that we calculated equal to the weight of M1? Well, when you calculate those values, they probably won't be identical. So how do we determine how similar or dissimilar they are? Well, you're going to calculate the percent difference. And once you do that, then you'll write a conclusion. And remember in the conclusion to state just very briefly what you've done, and be sure to include your specific results and specific findings. Be sure to include your percent difference values, and discuss some possible sources of error. And don't just put human error, and don't include your calculations as possible errors. Think of specific things within the experiment that could have led to the difference between your two calculated values. And as always, if you need help or if you have any questions, feel free to contact me.